This is sample 9-8, when molecules collide elastically, on page 398. So this involves some formulas that I'm not entirely sure if you'll need to be able to derive or what for the AP exam. I'll be looking into that for you guys. But for right now, we have in air at room temperature, a typical oxygen molecule moves at about 500 meters per second. The mass of an O2 molecule is 32 U, where U equals 1 atomic mass unit. So I'm just going to write this down. M1, so that's O2, so that's 32.0 atomic mass units. Now, I'm going to leave that there, and I'm going to explain to you later why we can leave that there in a moment. All right, the initial velocity of this puppy is 500 meters per second. Let's just say it's moving to the right because that's what it is in the picture. Okay, our second player in this drama is our hydrogen molecule, H2. It has a mass of 2.02 atomic mass units, if you remember your chemistry. And if not, they reminded you in the problem. It starts out at rest. Now, this already is a pretty unrealistic situation, but if we were talking about 2 billiard balls, it wouldn't be unrealistic. So let's figure this out. They're telling us that the collision is perfectly elastic. Now, that's helpful for 2 reasons. We know momentum is conserved because, well, momentum is conserved in a collision, but it also tells us that kinetic energy is conserved. So we're really just going to verify all of this, and there's quite a bit of plugging and chugging involved. But this is how you do this. So our conditions for conservation of momentum, or our equation, is M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. Now, a couple things we know here, that since the hydrogen molecule is originally at rest, this whole term goes to 0, and the others are unknown. But let's talk about why we can keep the masses as U instead of converting to kilograms, which would be annoying and messy because we're going to have like 10 to the minus 27th, right? If the U unit appears here and here and here, that unit's going to cancel out anyway, right? So in a problem that doesn't use kilograms for mass, if it's grams or pounds, even though pounds not mass, if the unit's going to cancel out anyway, you don't need to convert to kilograms. Just make sure that all of the units are the same. So if they gave me the mass of oxygen in U, but they gave me the mass of the hydrogen in kilograms, well, then I'm going to have to convert one to the other. But so long as the same unit appears in every term, it's going to cancel out. So that's why I'm going to leave the mass in atomic mass units. So this is our momentum is conserved statement, right? What about our kinetic energy is conserved statement? 1/2 M1 V1I squared plus, I'm just going to write 0 because V2I is 0, equals 1/2 M1 V1F squared plus 1/2 M2 V2F squared. So we have 2 equations, we have 2 unknowns, and so you can, through substitution, solve this, okay? And the reason we kind of get out of that we can't even do that is because this initial velocity is 0. So if you take a look at page 397 in your book, they even skip a few steps, but if you like to do this sort of thing, then go for it. What we get here is that the final velocity of object 1 is V1I times M1 minus M2 over M1 plus M2. All right, again, whoopsie, I took this formula from page 397 where they discuss a few simple cases of elastic collisions where one of the initial things is at rest. So again, it would have made more sense to talk about billiard balls in this example, but maybe since they already used it, or I did like the example with the atomic mass units. So for the first, the oxygen molecule, we get 440 meters per second, which should make some sense. It slowed down a little bit after running into the hydrogen molecule. The formula for the final velocity of the second object is V1I times 2 times M1 over M1 plus M2. Again, I got those from page 397. They come from solving these equations for V1F and V2F. And I get a speed of 941 meters per second, which again should make sense. The hydrogen molecule is pretty small. You should imagine that the amount of momentum that oxygen molecule sends that off at a pretty high rate of speed. So there's our final answers for final speeds for those two things. Now, really all we did was plug and chug some numbers, and that's really all we're doing for the rest of this problem. It asks us to confirm that the initial momentum is equal to the final momentum. I'm just going to write down the answers that I got for this. You can confirm them if you have the time, but realize you might be asked to do this on either my exam or the AP exam. The initial momentum of object 1 is m1 times v1I. I got 2.66 times 10 to the minus 23rd kilogram meter per second. Now, I converted that to kilograms, but you could get a different answer and use U instead of kilograms. But I converted. The final momentum of the initial molecule is 2.34 times 10 to the minus 23rd kilogram meters per second. The initial momentum of the hydrogen molecule is 0. The final momentum is m2 v2f, which gives me 3.16 times 10 to the minus 24th kilogram meters per second. And so P1I equals P1F plus P2F. So that does check out. This number here is equal to the sum of these two. And you can do the same thing. I don't think this came in ABC, but I just made it that way for the kinetic energies. The kinetic energies here is 1/2 m1 v1I squared, for which I got, 6.64 times 10 to the minus 21 joules. Now, in order to say joules, you have to convert that to kilograms. The final kinetic energy of the oxygen molecule is 1/2 m1 v1f squared. And I got 5.14 times 10 to the minus 21 joules. The final kinetic energy of the hydrogen molecule was 1.48 times 10 to the minus 21 joules. So you can see that the initial equals the two final. So we have confirmed, right? So if they ever ask you to confirm that this is elastic, what they want you to do is find the kinetic energies and show and say, since Ki equals Kf, the collision is elastic. So that's how you show that. So that's 9-8.